Okay, welcome everyone. Today we will be talking about perception, but first we'll finish up what we left last time. We'll finish up with maps, and I'll just quickly go over the ideas of layouts again, just to repeat the most important points here. So first, last part of the coding lecture, then theory on perception, color, Gestalt principles, and so on. Okay, so we talked about D3 layouts, and in your homework 3 you were already using D3 layouts. The big point about layouts is that they don't create graphics on the screen for you, they create derived data that you can then use to plot your graphics. So we had this example of a pie chart where the layout was actually creating for us a derived data object that contains angles, and then we used the D3 SVG arc function to plot the pie chart.
Could you make that bigger?
Okay. There?
Thank you.
So here you see this example of what the D3 layout actually creates. It creates an end angle and a start angle, and so this is what you then can use to draw the actual data. Then we talked about the force-directed graph layout, and here I kind of briefly introduced how a force-directed graph layout generally works. We have this forces, like we have springs to pull the nodes that are connected together, and we have repulsive forces between all of the nodes that counteract each other, and then we had the central force, the gravity, in the center of the screen that kind of pulled the network into the center and stopped it from drifting off. This is like a typical data structure that we use for graphs, and your homework contains a very similar data structure. You have a node list and you have a link list. In this case, the link list has indices on the node list. So we have source 1 to target 0. And we have additional attributes in here. And then we played around with various properties of the force layout, like charge or link distance or friction or gravity, and so on, and we saw the effects of that. And then the key thing about the force-directed layout was that this is an iterative algorithm. So you don't have an optimal result at the very beginning, but you have to run it multiple times. And that's what this tick, this force on tick function does. So this is actually, like here we only create all the stuff, but here we actually position it. And this tick function is executed until the network cools down. So this is like a parameter of D3. I will simply check how much change is still going on in the layout. And if this change is negligible, it stops calling this tick function, and you reactivate this tick function if you change anything. So for example, if you drag a node or something like that. Yeah, so this is the example. And then I briefly mentioned that there's many other layouts. For example, tree layouts are very valuable. So like you have node link diagram tree layouts, you also have tree map layouts, you have sunburst layouts. And I will talk about these when we talk about the actual visualization techniques, but you can simply go to this link and take a look at all the different layouts that there are. So let's just take one brief look at the chord diagram, and this will create like these chords that connect to, in this case I think it's genome. So this is a circus technique, like this technique is called circus, and it shows you translocations on a genome, for example. And so this layout can also be, you can see this is, the code isn't really super long here. So you can use this kind of layout to create those diagrams. And there's many, many examples, so I'm not going to go through the details of the layouts. So any questions about layouts before we move on to maps? Okay, so maps. We kind of already drew our first map last time. The important thing to know about maps is that they use a special format, the GeoJSON format. So first we kind of distinguish between, do you want to plot data on a real street map? Then would you have to use something like the Google Maps API, or do you want to create data maps like choropleth maps, or maps where you plot circles for cities or something like that? Then you would use D3 and the GeoJSON or the TopoJSON format. And the GeoJSON format is a JSON format that essentially describes shapes, and these shapes are typically geographical. And this here is an example of this GeoJSON format, and you have one of those in your homework too. So you have a feature collection, and then you have the individual, like an array of features. You can see like this here, the array starts, and then you have this entry, and here you have like an entry of type feature ID 1, and the property is name Alabama. So this is the shape of Alabama. And then here is the actual geometry. It tells us which type it is. It's a polygon, and then we have the longitude, latitude, coordinates here listed. And so these are essentially just the points in longitude, latitude, and then D3 uses the geopath function here to create these shapes. So that's the basic idea. So we had this very simple example where all we did was read in create a new path generator, load in this US states.json file, and as you probably remember, we had this discussion about how we read data in an asynchronous fashion last time. So here we actually d3.json executes asynchronously, and we have to essentially give it a callback function, and we do this inline. So we define the function that is called when this is completed and this is loaded in here. So this function takes a parameter JSON, which is the loaded data, and then what we do is simply we do this standard drawing, like SVG, select all path, we map the data, then we append the path, and then we draw the path. The path is given by the D3 geopath and uses the data that is mapped to the SVG element here, or to the path element here. So that was pretty simple. The result was this map, and of course it applies some styling. So this has no fill, it has a stroke, and we have a stroke color. So this is the map that we saw here. But one thing about maps is this is just really using latitude, longitude coordinates. And one thing where we kind of stopped last time was that if we talk about maps, we also have to talk about projections. And the thing is that, of course, the Earth is a sphere, and we kind of want to display this on a flat surface, in this case on a screen or on paper. So we have to find some kind of mathematical function that maps us the surface of the sphere to a flat surface. And this is, of course, an ancient area of geography or math, how you can map the sphere. And there's many, many different functions. In this case, we're really just plotting latitude, longitude, but you can see that this is clipped here, so well, of course we could refocus this, but you'll also notice probably that this is not really the latitude, longitude of Hawaii and Alaska. So what happens here is that D3 uses a default projection. It uses the Albers USA projection as default. So when I don't specify a projection, it will just take this one. And if you try this with a world map, it's going to not result in great, it's going to not look very pretty. So what we need to do is we need to specify, for all other cases than the US, we need to specify these projections manually. So here we are defining the map projection. We have these many projections here, and then we are also translating it to the center. And here we are setting this projection that was defined. And here I look at the Albers projection, which is of course suitable for the United States. So that looks nice. And now let's see what happens if I change this. Neutral equal area projection. And so here you can kind of guess that we are kind of drawing a sphere and not showing everything here. That's of course more interesting with a world map, or we could do this conic equidistant projection and so on, but it doesn't really look that great with the map we have here. So let's take a look at this showreel. So these are all the different projections that D3 supports, or some of them. And this is always the same data, just apply different projections. So this is maybe a little more than what you would really need. But you can. You can do this. We will talk about which projections are great, which are not so great in the lecture on maps, but just basically there's a couple of things that you have to think of. A, is it, does it distort the surface area? Does it preserve angles, which is important for navigation? So like Mercator, for example, preserves angles and is really bad for preserving the areas. So it's kind of being critiqued heavily for being like the North and the industrialized nations kind of make themselves bigger than they are compared to, like, for example, Africa is really protection. But Mercator was really developed for navigating at sea, and for this purpose it's a good map, but for other purposes it's not a good map. So we'll talk about these maps in the lecture on maps. Okay, so what we need to know here is simply how to use them. So like here we define a projection, then we translate it to the center. The path generator here is exactly the same call as we had above here, with the only difference that we also specify projection, so it doesn't use the default projection. And now we again just load the data, bind the data, and then append the path and draw the path. And that is it. Okay. So next, we will talk briefly about the choropleth map. And the idea of choropleth maps is really that you simply, it's not colorpleth map as you would maybe hear, but it's choropleth map. We'll also talk about those later. And the idea here is that you take geographic features and color them somehow, which is very common. And in this case, this is color-coded by economic output. No, not by economic output, but by agricultural output. And I'm a little bit surprised that everything is green here, but well.
So the darker areas are the higher producers?
Yeah, but this doesn't look quite right to me. I don't know why.
Yeah, it looks like a lot of the states have the same green.
So the color map might be off. Yeah. So this is some problem with this particular. Yeah. So this looks better. I have no idea what happened here. So yeah, you can see that California produces has a lot of agricultural output. Utah doesn't have a lot, and we don't have data for Alaska, Hawaii. But yeah, you get the idea. So let's look how we do this, and this is actually pretty simple. So conceptually, all you need to do is to set the fill of the path that you're drawing it to the right color. So the challenge here is really just to merge the data, because typically you don't have the GeoJSON file doesn't come with all the varieties of data that you can think of. So what you need to do is you need to integrate the data with your GeoJSON file so that you can bind it in one place. So that's what 90% of this code here does. So here we just set up a color scale with this certain range. And then what we do here is, like, we first call the GeoJSON, the US states JSON file. So here we loop them through all of the states. No, this is the agricultural data, sorry. So here we load the agricultural data first. Then we set the domains, we set up the color scales. So, and then we have within this function we also call we load the GeoJSON file about the US states. And here then we loop through all of the states to actually assign the data. So here we go with, look, this data contains the agricultural output for the countries, and like here the data of I has the object state, and data of I has the object value, so how much of agricultural output is there. So we kind of read this to data state and data value, and then we go through the JSON to the GeoJSON file and simply set it to the proper, like add an additional, like this here is the interesting line, we set an additional property where we like if the data state matches the JSON state, we set it to the correct value. So what we have in end effect is that we have augmented this GeoJSON file with an additional variable, and we use this variable here then to actually fill the data, fill the polygon with the appropriate color. So if we don't have a value, we return simply this gray, and if we have a value, we return the color that this color scale gives us. So that's how you do a choropleth map. So really, it's just about data preparation. Of course, you would do this. You could do this offline. You could do this once. So if you want to do an example that you host on a website, you would do this once. You don't have to use JavaScript for that. You could use anything, and then you would have this augmented file, and then you could simply draw that. So any questions about this example?
It doesn't seem like it would be much of a performance hit with a small data set.
No, but it's still something, well, you can do it on the client, it's not a big problem, but you definitely shouldn't do it every time you update. Yeah. So you should do it on load. Okay. But I would probably still create a derived JSON file and save that.
Okay.
But yeah, it's not expensive. Okay, so then finally let's go through top of maps. So like what we want to do is we want to create these circles, and this is kind of similar to what you're doing in your homework. We want to create these circles with large cities in the United States and set their radius dependent on the population. So you can see New York is the biggest circle here, and then we have Los Angeles and Chicago and so on. Okay, so what we do here is we again have set up our projection. We again load the US states here, and then we also have a data file that contains the US cities. So all we need to do here is load these again in a callback function, and then map the data. So here we map the data of the cities, and then return a function. Then we return essentially the longitude and latitude of this particular. So let's take a look at the US cities file. So we can see what we have here is we have ranks, we have places, we have the population, and we have the coordinates, the latitude and the longitude. And then what we're using is latitude and longitude to position the pixels, and the population to set the radius here. And we're not using the rank or the place values. So how this works is we simply call this projection function for the circle and pass it along the longitude and the latitude for x, and then we do the same for y. Then here we simply define the radius based on the population, and match, we use the square root here to kind of not make the circles completely pop out. And this is basically it. Here we fill it with blue, we give it an opacity so we can see these overlays here, for example, in that area. And that is basically it, so pretty simple again. So first drawing the map, and then drawing on top of the map, pretty much independent of the map. So for example, we could throw this out, and then we would just see points. So we can draw these points completely independent of the map, of the path. We will just use the same projection function here and use the longitude and latitude for that. That is it, and this is also how you can plot the places of the games in your homework. Any questions about that? Okay, so that essentially concludes our introduction to D3 and JavaScript. I might do another lecture on code when we talk about designing larger systems. We will see, maybe to go together with homework 4, depending on whether I think it's really necessary. But this essentially concludes the technical introduction. So if you have any extra questions about JavaScript or D3 and so on, you're welcome to come to my office hours, or you're welcome to go to the TA's office hours and work with them. And you will, of course, be continuing to work on D3 related things in your homeworks. But now it's time that we really start to talk about how do we create a good visualization. So the idea is that you now have the craft to develop those, and now we will talk about the science and the art, what makes a good visualization. So basically you can draw a lot now, but the next, like the rest of this lecture will be about what should you draw. Okay, so then let's switch to perception. First, a couple of words on administrative things. You received your grade for homework 0 and 1, so you should have gotten an email yesterday. Homework 0 had a pretty good average with 9.53, so most of you got 10 points, and only a couple of people got 0 points because they didn't set it up, but remember this is only 2% of your grade. Homework 1 average was also very high, so 8.72, and you can see the distribution here. It's like the largest majority, almost 70 people, got more than 9 points, and there's a couple of people who got 0 points. Maybe they didn't submit, they dropped, or we still have an issue with reading your Git repository, so we will resolve this if necessary. Any questions about grading, about the procedure? If you didn't receive an email, please get in touch with us. But if not, homework 2, homework 3, remember it's due this Friday, so use the resource. Sorry?
Next Friday.
Next.
The schedule says
It's
the
not
25th.
It's not this.
Really?
Yeah.
Okay. I thought it's this Friday. Well, if the schedule says it, then it's next Friday. But do use the lecture resources and recommended readings. Ask on Piazza if you have any questions, and go to the officers. And I'll have to look up what happened here. But I'm definitely not going to shock you now. Okay, so this is about administrative things. Let's talk about perception. So, why do we need to talk about perception? Well, it's about, like, visualization is really about producing content that you see. So we need to understand how we see and what we see. We're not going to go into details. Of course, you could do, like, you could spend a whole career on studying human vision. But I will just give you a couple of important pieces of information that will help you design your visualizations and have some fundamental understanding of what is going on. So there's two different things that are important to distinguish. This is perception and cognition. So perception is essentially the identification and interpretation of sensory information. So you have like this physical stimulus, and then you go on to recognizing information. So your perception is shaped by learning, memory, and expectation. And cognition, on the contrast, is the processing of information, so applying knowledge. So, for example, I would perceive a ball, but then I would kind of think about what can I do with this ball. So, or I could kick it, and this ball can roll, and so on. This is something that cognition does, and perception tells me, okay, this is a circle first, and then it tells me, okay, my experience tells me this is a ball, it's a sphere, and I can interact with it. So, one interesting analogous piece is that if you hear somebody speak, that is perception. So if you hear somebody speak in a language that you don't know, you still perceive the words. But if you understand the language and the words, and you think about it, then this is actually cognition. Perception is really about things like the eye, the optical nerve, the visual cortex, about like the fundamental things like bright and dark, or effectual perception. Like the first processing, you recognize edges, shapes, and plans. planes, and it's not conscious, and it also like steers your reflexes. If somebody tries to punch you, you don't have to think about how to react. You kind of like immediately have a reflexive reaction to that. And cognition is really about recognizing object, abstracting, what can you do with these objects, what are the relationships between the objects. It's about conclusion drawing, about problem solving, and about learning. So this is an interesting example of the difference between perception and cognition. So you have all these words and they're colored in a certain color, but it's not the same as the content of the word. So like if you read red, this green word red here, you kind of like, if you need to abstract and understand what I mean, if you read the text, but it still is green initially. There's also a difference between looking versus seeing. So it's really important to understand that what we see depends very much on the environment of how we know it. So there's constant interpretation, and this is like the theme that we'll follow. Everything you see, like there's a big difference between the raw information and what you make of it. So for example, who of you can see something here? Like just raise your hands once you spot it. Something. So I see there's less than a third of you who have already recognized something. Like just, who doesn't see anything? Okay. So once I tell you what you can see here, you will always see it. You never can go back to not seeing it. So here's a Dalmatian, a dog. You can see the head here, the legs here, the front legs, the hinds, and here's the back. Still can see it? It's a Dalmatian, a dog. A spotted dog. Maybe this is the resolution isn't very helpful here. But here, here are the ears. Here's the head, here's the neck, like he's pointing this direction. Here are the legs, here's the body, and the hinds. So, there's, like, this is of course a constructed image and the resolution isn't that great here, but just to, like, we interpret things that are, like, we interpret shapes a lot. So this is called perceptual hysteresis, or the effect that you cannot unsee this anymore is called perceptual hysteresis. So once you have understood it, you can't really go back to not seeing it anymore. Here's another example where we see something and given our understanding of how the world typically works, we are fooled. So we can see like this image and it looks like there's a three-dimensional shape of like a cartoon character swimming here, but if we change perspective, then we immediately recognize that this is not in fact like our visual system kind of fooled us. And of course the comic appearance gives it away here, but still we kind of perceive it as a three-dimensional object just because we're trained to perceive three-dimensional objects. So we rely on priors, we rely on our understanding of how the world works in our processing of information. And here's a couple of examples that kind of make us think twice and that kind of like don't really work the way we expect things to be and therefore they're kind of funny. And then, as you saw with this dog, we always have to, or we have a tendency to interpret things and interpret shapes and see things that are not really there. So for example, everybody sees a cloud that is shaped like something occasionally. And this is especially strong for faces, so here we have like a little cucumber that is a face. Of course everybody, like there's people that see Jesus in a toast. And here, like these chairs look like faces, this apple plug looks like faces, and then you could say this is a deep in thoughts, deep fryer. So of course these are not faces, but our visual system is primed to recognize faces because they're important for us. So we do recognize the shapes, and this effect is called pareidolia. So what you really should, like, the point of this is that vision is constructed top-down from the input. So what you see, when you see a thing, depends on what the thing is, but what you see the thing as depends on what you know about what you're seeing. So really it's like the raw sensory input is only half the thing. It's really important to understand how we put it into context. And of course there can be cultural differences here, for example. So let's briefly talk about our sensory instrument, the eye. And I'm not going to tell you much that you haven't learned in high school biology here. So you have the lens, and you have the retina here, you have the optical nerve, so essentially the image is like projected here onto the retina, and then here are the rods and cones that perceive the actual signal and then translate it to you, or then process it and pass it on to your brain. So the thing that is interesting about this is the understanding of our color vision and of our black and white vision. So we distinguish between two types of sensory cells. These are the cones and the rods. And we have a lot more rods, so we have about 120 million rods, which are really great for black and white seeing. And we only have a few cones, so we have 5 to 6 million cones. And these are really used for color vision and for super sharp vision. And they are less sensitive to light, so that's also why we don't perceive colors when it's dark. But they are responsible for our sharpest vision. So you can see here is given like the angle from the foeva, this spot here, where you can see the sharpest. You can see like how dense the receptors are accumulated around the foeva. So we have like the most of our vision receptors around the foeva, and then the further we go away from the foeva in both directions, the fewer receptors we have. So like we see, like if you hold your hands there, you can perceive there's something, but you couldn't tell whether your nails are clipped. You just can perceive that there's something going on. So in the foeva itself, we have 27 times the density of. So like this is really where the super sharp vision happens. And we only have the cone cells in the foeva. So this is how this looks like. We have the rods that are sensitive to black and white, and they to the brain. Here's a microscopic image, so you can see the rods and the cones. The rods and cones and so on, so the cones do have a different, like there's different types of cones that have a different sensitivity, and that's also how our color vision works. So we have cones that are responsible for perceiving, or not responsible for, but they react different to stimulus that is on the red wavelength, and the green cones react different to the stimulus of the green wavelengths. And so it's not like only green attracts like a stimulus, but it's like how this is balanced, how we perceive the colors. And you can see, like we'll talk about color blindness, so if you're red-green blind, you're actually missing one of those types of cones. Here is an interesting plot that shows you the distribution of rods and cones. So here, like again, we have the foeva, and you can see that there is only very few cones in the periphery of the eye, but there is really a lot of cones in the foeva. And here we have the blind spot where the optical nerve leaves the eye, so you can do these experiments where you can actually lose your finger when you track it. And so here is a microscopic image of the foeva, and here of the periphery. Of course, at different resolutions in this case. And here are the responses of the 3 different cone types, like blue, green, and red, so you can see like which wavelengths they react to. But what you should note here is that there's no reaction to a blue stimulus of a red cone. We just see like red is less well, what's the word? Stimulated when you have a blue wavelength or a wavelength in this area here than blue is, for example. So this is how you actually see things. You see things like you see one spot sharp. Of course, the reason why you perceive this here as fuzzy is because you navigate around. So your eyes, like if you just were close up here and looked at this spot, this would actually look okay to you. But as soon as you start moving your eyes, you of course see that it's blurry. but this is really how you should think of people see, for example, your computer screen at any given time. And the reason for this is that we work in the reason we perceive this blurry image here, so we can see that this is actually pretty blurry, is because we kind of like quickly move our eyes around in an alteration of fixation and saccades. So fixations is essentially you maintain the gaze on a single location and then you actually perceive it. So this lasts about 200 and 600 milliseconds, and the saccades is when you move between the different locations. So here is a graph of each of these dots represents a fixation, and each of these lines represents a saccade. So like, and the colors represent, I think, could be multiple users. I don't exactly know for this particular image. So what this tells you is, like, if you look at an image first, you start to scan. Typically, if you look at the picture of a person, you start to look at the face and at the eyes. Then you move around, and then you can see, okay, many people look at the face and the eyes. Many people probably come in here from the right, and then they start to look at the other dominant features here around the hands. And here's something else that is has a high contrast, so we're probably attracted to that. So this is essentially how this looks like. And I have a video for that. And these videos wouldn't embed. So here's a heat map of how people perceive, like where people look in a video. So you can see that you can use this to test commercials, but you can of course use this as in research. This is done with an eye tracker. And you can always see that we focus on like things like titles, at text, and at eyes and persons, say faces and so on. This is what happens when you play karaoke. So this guy is actually recorded via an eye tracker, and he's played this stimulus, so he doesn't see this interface, but this is... So you can see how it works when you read text. Brave soul. So this is a different mode of this eye tracker. Yeah, it's not so important. And you could see briefly that since this person's face came up, he actually looked at it, even though it's not relevant for his current task. Okay, so this is again a different representation. Ironically, this is not a good color map for a perception study, but well. Yeah, so our vision isn't similar to a camera. Like a typical camera, unless you have depth of field effects and so on, captures everything in focus, but we don't. Like I kind of mentioned this already. Like a camera would, like if you look at these two reporters, the camera would capture all of them in sharp detail. But we actually don't. So we really do this like essentially our system is a little bit lazy. We only process the information that is really relevant or we only can process the information that is really relevant in high resolution. Yeah, so you could think of vision as an ongoing construction project. So you kind of like, you don't see everything at once, but you see, like you build up piece by piece. This is how an eye tracking experiment can look like. So I don't know whether you have ever participated in one, but you essentially have infrared spots that shine into your eyes and that kind of make your pupils lighter and make them brighter. You don't notice anything. And then you have an infrared camera that tracks exactly where your pupils move. And those things are really, really super fast, so you can see every little detail. And then you have this aligned to a stimulus, which is essentially typically a computer, could also be paper. And some of the models, like for psychology research, if it really needs to be super precise, you would even have to like screw your head in. But for, let's say, user interface experiments and so on, nowadays these tools use head tracking, so you can even move around your head, and then you have a less, let's say, restrictive environment, and you can do a longer study without people feeling too uncomfortable. There is now also eye tracking devices that you can mount as glasses, so that you could like go through a supermarket and try to understand what people look at, or that you could use, for example, to study if you're in a, like user interfaces in a virtual environment or something like this. So it's pretty cool what you can do there, and it's also very interesting to see the results. And I've done a couple of studies myself where I looked at how people perceive the visualizations we designed, and this always was interesting. Like we could always tell something interesting about it afterwards. So I'll show you an example later. Okay. Yeah. So this is what the computer essentially sees: is like a creepy picture of your eye, and then by using computer vision methods, it can actually track where you're looking at. So at the beginning of the lecture, I kind of already mentioned this, this idea of that things that we perceive is not necessarily what they are. So we don't have a general purpose vision. What we see depends really deeply on our goals and our expectations. So we are good at relative judgments. So if I hold up those two things close to each other, you can easily tell this one is bigger than this one. But if one was over there, you wouldn't be that good at it. So it's always, or if I show you this one today, and next time I show you this one, you wouldn't be as good at it too. So you're good at relative judgments, but you're less good at absolute judgments. And then, whom of you have seen this Ames room? Yeah, so this is an interesting illusion. So you perceive, like here is essentially a dwarf, and here is a giant, and this guy looks about right. And interesting is how this works. So once we change the viewpoint, we can actually understand what is going on. The room is distorted, but like we know from our experience that rooms typically don't look like that. So we kind of like assume we have this relative judgment. This person, like this must be a regular rectangular room, and thus this person seems to be shrinking and increasing in size. Yes.
Is this a consequence of living in a carpentered world, or do people from, who are living in labs experience this?
So it's not directly a consequence, but for this particular example, yes, of course. So like we look, but if you can use natural features the same way, but of course, like we perceive things rectangular, we have a conception of how big doors are, we have a perception of how big windows are. So if you were to do this study with somebody who has no idea of windows and doors and that they are usually rectangular and so on, that wouldn't work, but you could easily construct an experiment that uses this person's experience. So like the specific effect, yes, is based on our experience, but of course generally speaking, no. Yeah, so like you saw this diagram here, but we don't have to talk about this. So one important thing that we will use a lot is color. And color is pretty complex. So again, color is something that you can spend your whole life studying. And I will also only touch on, I'm not going to touch on the physics of color. I'm only going to touch on the perception of color a bit. I will just give you like the most important things that you need to know about color. So color is the visible part of the electromagnetic spectrum. So you essentially have electromagnetic rays in the wavelengths of 390 to 750 nanometers. The spectral colors are evoked by a single wavelength. So we have spectral colors and we have colors that are combined of multiple wavelengths. So they are kind of unsaturated colors. So these could be achromatic colors or mixes of multiple wavelengths. For example, purple or magenta are not here on the spectrum of the single wavelengths, but are actually combinations of multiple wavelengths. So you can see like we have gamma rays, X-rays, ultraviolet light, and only this tiny fraction here on this logarithmic scale is actually the visible light, and this is like this rainbow color map that we will talk a bit about. And then we have infrared light and radio waves. So color has a couple of dimensions. So first it has hue, and this is actually, if we just talk about color in a colloquial sense, we usually mean the hue. So like these would be the different hues, but then it has also a saturation, like how pure is it? Like for example, here we would have different saturations of red, different saturations of purple, and different saturations of blue, going from gray to more of this color. And then we also have the value or the luminance or brightness, and like color terms are really not a little bit messy, but we will use this hue, saturation, value, or sometimes brightness. So this essentially tells you the lightness or the darkness of a color. So high saturation colors have medium values. So you can see the different saturation examples here. So like this is a high value and low saturation. And so people try to describe these, the color space in the, for example, in the CIE Color Model. Here we have these chromaticity diagrams, and these chromaticity diagrams, they're a little bit complicated to read, but essentially the outer curve here is the wavelength of color, and in here are the various combinations. So the pure colors are along this curve here, and in here are the different combinations of these wavelengths. And this is important for us to understand because this is how screens work. Like we have a typical computer screen has red, green, and blue pixels, and so how this works is that the green pixel and the blue pixel and the red pixel has to be situated somewhere within this gamut. So your computer screen cannot actually show the full spectrum of colors. There are certain colors that you can't display faithfully in a computer screen. You probably have noticed these super highly reflective colors that are used for warning signs and so on. They don't quite look the same if you take a picture of them. So this is an example of where color is lost. So if you have a 3-pixel monitor, like a 3-color monitor, as almost all of monitors are, you kind of always have this triangle of the color space that you can actually use. So you can see a couple of different color spaces down here, and this is a bit hard to read. Well, we have sRGB here, we have Adobe RGB, then we have this CMYK here, and then a hexachrome in yellow. So depending on like what your printers can do or what your screen can do, this is different, and that's also why colors between different screens look different. So if you, for example, work in design, you will have to calibrate your monitor to a standard set of colors. And of course, these primaries are arbitrary, so I could pick those 3 points wherever I like on the gamut. Of course, typically you try to pick them to have a wider color range as possible. So there's 2 different ways to create color. It's either additive or subtractive. So like if I were to project colored light, it's additive. So if I have a red spot, a green spot, a blue spot, and they use different wavelengths, and if I overlap those spots, I have this additive color mixture. So you can see green and blue has this turquoise color here, the overlap between them, and if I actually mix red and green and blue at the same intensity, I get white light. For subtractive color, this is essentially what we use in print. So the pigments reflect the color, so you have the subtractive color model, so you can't, by adding color to, like pigment, to paper, you can't produce white color, so you have, well, of course you can use white pigment, but by using these three pigments, you couldn't create a white color, so you would essentially, by mixing magenta, cyan, and yellow, you would create dark colors. So this is the additive color, additive versus subtractive color mixture. So in this case you use light, in this case you use pigments that absorb light. And of course for us, since we're working on a computer, mainly this model is more interesting. And interestingly, color vision is not super important for our daily vision. So we would be fine to survive if we don't see color at all. So it doesn't help us to perceive the layout of objects. It doesn't help us to understand how things are moving. We also can understand the shape that they are, and so on. The interesting thing is, though, that color breaks camouflage, and that's one of probably the evolutionary reasons why we can see color. In this case here, the black and white picture, we couldn't see the red cherries, but here we can easily spot the red cherries. And it tells us also about material properties, and like one theory is why color vision developed is that we can simply judge the quality of food. So we can see if some apple is rotten or not using our color vision. In visualization, color is of course often used for labeling, and we will talk about this next lecture in detail. Here is a picture of, like, that is really, there's a lot going on that is wrong here in this picture, and you probably can barely see it. Well, so this is a little bigger maybe. So this is a visualization of the internet, and it uses like 20 different color scales, and it uses almost 5 different shades of green, for example. And of course you can tell this is brighter than this one if they're next to each other, but you can't really tell if this spot here is this type of green or this spot here is this type of green. So like this is also a hairball, a graph, and we'll talk about this too, but this is not a good visualization technique. So like as a rule of thumb, if you want to use color labeling, use about 6 colors. If you have significantly more things that you want to label than 10, you shouldn't use color anymore. So you could use something else. We'll talk about that later, or next time. And I've talked about this color brewer tool in one of the D3 lectures. These are carefully designed color schemes for various applications. For example, for labeling, for nominal data, but also for continuous data. And these are carefully designed to be applicable to various circumstances. So you can specify, like, I want this to be to work on in print, I want this to be colorblind safe, I want this to be, I can actually photocopy it and still can read the data and so on. Of course, if you want to photocopy this picture, you won't, like in black and white, you won't be very happy with it. So I'll talk more about this another time. But for quantitative data visualization, so if you have a continuous spectrum, you should always use value. So you shouldn't use hue. The saturation works also, but it doesn't work as good. And the problem here is, like, here, you imagine this is a continuous data set from 0 to 1. Okay, and here we're just using value, so this gets brighter. And so this actually represents the data pretty faithfully. So you can see 0 is black and 1 is white. But here in the rainbow color scale, as a lot of science applications, especially a couple of years ago, still used it, you see a lot of gradients that are simply not there. So you would think that there is something interesting, an interesting feature here, or there, because there is a sharp boundary. But this boundary is kind of arbitrary. So you can see here's a couple of different examples for different data sets. Like here you would see a faithful representation of, like, if it's circular, like high to low. But in the rainbow color scale, again, you would perceive this gradient very strongly. Here are two examples. Here on the one, like this is a flow visualization that on the one hand shows you this using your rainbow color scale, this flow, and on the other hand like this blue-yellow color scale. And sure, you can see like the outliers, the brightest spots pretty well here, but like this kind of fools you into thinking that the surrounding area here is actually much lower, which it is not. And so here is a color, like lighting examples that are kind of show you just how arbitrary rainbow color maps look like if you use it to define a color map. But people also did very fundamental experiments, like testing how our perception of a change in value on the color scale depends on, for example, in this case, luminance, a luminance color scale. So here, essentially, you can see the error. Here on the Y scale is plotted how big the error is between two different steps, and you can see like people are not very good at this very dark areas, but then this is actually pretty good. We see that the error is relatively low consistently across the rest of the color scale. Whereas if we use the same data set and the rainbow color scale, we can see that the error is pretty big, especially at this where we have these essentially arbitrary gradients here. So if you have continuous data, you always should use like a color scale that is really well designed, and you should typically not use multiple hues. Of course, you could have, let's say, values smaller than 0 and values bigger than 0, then you could use multiple hues, but don't make any arbitrary gradients in your color scale. When you design visualizations that use color, you should also think about color blindness. It's actually much more prevalent than you think. So I can tell you right now that there's a couple of people in here that have at least a red-green color weakness. 10% of all males have a weakness in perceiving red-green colors, and 1% of all females. And this is probably due to X-chromosomal recessive inheritance. And the reason is simply that we have, that colorblind people have a lack of medium or long wavelength receptors, so the cones, or alto spectral sensitivity. And most commonly, this is a green shift. So this is how somebody with normal color vision would perceive this rainbow flag. If you don't have any green receptors, you can actually distinguish those two colors, and this color looks exactly the same to you as the red color. And if you don't have any red receptors, this is how this would look like to you. So it's important to design your color scales so that people, at least with red-green blindness, don't suffer from it, because you're essentially excluding a large percentage of your audience. When you do studies, when you want to test like a visualization technique, for example, you also have to apply a color vision test. So I'm not going to ask you to raise hands, we can see the numbers here. But these are the typical color blindness tests, so you should be able to see numbers in these spots. And they're designed so that you could spot which kind of color blindness people have. So here it would be like a 7, a 6, in the second one on the top, then a 26, a 73, a 71, and a 45 at the bottom right here. It's 7, 6, 26, 73, 71, and 45.
74, is it?
What?
74?
45. 71.
So I see it as 7, like from left to right, from top to bottom, 7, 6, 26, 73 or 13, 71 and 45 or 46. 45 would be. Yeah. So these things are hard, but they're designed to be hard, and they're designed to make you think twice. Of course, like this setting, like color on a projector is always not that great. It's a little easier if you have like a color-proof printout of that. Here's another example of how people with various color deficiencies see the world. And there's actually, just recently I saw that there is now glasses that can correct some of the some color blindness effects, which is interesting, but it's probably not something that we will be able to rely on for visualization. So this is an example of what happens if you use colors excessively. So if you have normal vision, you can still distinguish those, but if you are red-green colorblind, essentially you lose a lot of your visual vocabulary. So you should really be aware of that. And here is an example of the New York Times. This will actually be a future design critique, and here they use red and green to visualize reductions and increases in the US budget. And so this was actually also like a side story. This was the first visualization that the New York Times did that used D3. And so you can see these two circles here, like this is an increase in spending, this is a decrease in spending. If you're red-green blind, you couldn't see the difference here. So it's really like especially if you're targeting a mass audience, you shouldn't do this. Well, this kind of, I feel like the situation is getting better, but still there's a lot of work to be done here. There's a website where you can actually go and upload your visualization, or a picture of your visualization, and check how it actually looks like for colorblind people. So you can actually simulate the various color deficiencies, and you can take a look at whether you can actually see what is going on. A couple of other terms. Let me just check how we are doing on time. Okay. Luminance, brightness, lightness, these are things that you will encounter occasionally. So luminance is the measured amount of light. Like if I have a sensor and I try to measure the light, it would be measured in luminance. It's luminous intensity per area. Brightness is the perceived amount of light. And those two things are not the same. And lightness is the perceived reflectance of a surface. So this would be like lighter than, let's say, the blackboard. And we also have a thing of the that we think of as the lightness of a color. It's also important to understand, again, this context is always very important in our vision. So the perceived brightness of an object is relative to its background. So here we have examples of these rectangles always have the same color. But we perceive them as very different depending on the background. So here we perceive it as dark, and here we perceive it as light. And of course, this is also based on our experience. Like things that we know because of the lighting situation that should appear darker, we kind of like correct mentally for that. But sometimes, especially in these artificial scenarios, as we do them in visualization, this is not actually correct. And then you also have this this illusion. So this is what the data actually does here. Like it's linear steps, but you perceive it like with these increasing slopes here. It's also an interesting illusion, which some people also use to, or which you have to be aware of, especially in computer graphics. And then you can use the corn sweet effect to do edge enhancements. So this would be essentially like if you plot this linearly, you show essentially edge by increasing it, going down and increasing it again. And here is a picture where this is done nicely. So this is something you could do to make objects more distinct. And you can see this in user interface elements very commonly. So if you go, for example, to GitHub, you look closely, all the buttons are separated by this corn sweet effect type thing. This is an issue, and this is maybe like, this slide is interesting, of course, for people from Utah, because font shading was developed at Utah. So why is this an issue? It's not too much of an issue in computer graphics, in visualization, but it is an issue in computer graphics. So this can result in large areas of judgment. So if you have like an approximate shape that you use polygons, and you have like a scan line here, and if you just color these uniformly, then you would have a luminance profile like this. But this is actually perceived even stronger, like with stronger differences. If you have this smooth luminance profile that you're using Goro shading, this is kind of improved, but you still have these little peaks. Whereas font shading takes this into account and produces this nice gradient, essentially. So this is just a side note. This is interesting for people that are interested in computer graphics, not too much an issue for visualization. Here we have an example of the corn sweet illusion. So we perceive the upper part here darker than the lower part, but when I actually add a rectangle that avoids this shading effect here, we can actually see that those two are in fact the same color. So you can see this looks white to you, this looks gray to you, but this is just because of how we interpret lighting and how we interpret shading and so on. So if we kind of remove this shading effect here, and then we can actually see that those two are exactly the same color. There's a couple of other interesting examples here. Wow. Well, I should have checked this today. It was there a couple of months ago, but I'll update the link. Let's see. Here we are. So how this works is you have a couple of those interesting effects and examples, and then you have an interactive demo here where you can essentially add something that actually removes your bias. So you can see you perceive this as darker, you perceive this as lighter, and if you add a neutral element to it, you actually perceive it exactly the same. Then here you have this dot, which looks like it's getting brighter and darker as it moves around. But if we add a neutral surface, we can see that it actually stays exactly the same. Here is this particular corn sweet effect that I showed you before. There's other of those shadings, and there's also things that are relative for that are important for colors. So here we perceive this as more red and this is more brown, but if we add a neutral element to it, we can see that this is actually the same. So you can play around with this if you're interested. I'll update the link so that you can actually find it. Okay, so let's take the last couple of minutes for a design critique. We have 10 minutes, so let's be brief. Let's do a 5-minute discussion. So I'll just give you the link. First link is to this sheet. Yeah, again, do this in teams of 2 or 3 people. Just take a look at the...
This will share. Yeah, that's fine. I'm gonna grab that chair. Wheel on up here.
In this case, it is actually important that you go to the website.
The same should go to the website.
I'm guessing that if you're colorblind, that would be just dots of all the same color.
I am. It's pretty close.
You have a red, green.
I have a slight red-green sensitivity.
So this is interactive. You should look at it on the website.
Where's the link again? again?
It's on the paper,
Oh, okay.
but it's also here.
It's right here. Really confusing.
Right.
Further from the New York Times, we know who this is for.
A lot of our cars driving around.
It's cute. Okay. So we can guess that just general driver age population people are the audience.
Yeah, if you own a car, drive.
Drivers slash car owners. What questions is this visualization?
Well, no, like, to me it seems all over the place because of the fact that all of this, it's trying to like tell a narrative, like if you click through the little tabs, but it doesn't seem like, I don't know, it doesn't seem like it's all related. Some of it seems like we're talking about this thing, and we're telling a different story on this page, so I'm having trouble figuring out what it's its overall message, I guess, is that there are a lot of recalls.
Yeah. I think it's trying, it's like a linear Venn diagram.
Yeah, sort of.
It's taken a Venn and just splattered it and pulled them apart.
Yeah, I guess I can see what you're saying.
So I guess you would say it would be trying to answer general car recall by category or by different groups.
Okay, so we don't have a lot of time left. Let's briefly talk about this visualization technique. So, what is the question, what is the data that we see here? What's the question that this visualization tries to answer? Yes? So, why do you think that they made this visualization at this point in time?
Probably because of the Takata airbag recalls.
I couldn't, sorry.
Probably because in large part of the Takata airbag recalls.
Yes. So we can see in the histogram up top here that there is a significant spike in 2014. So, what do you think about the use of animation here? Like, this majority of the screen here are little cars driving around.
It's kind of distracting.
It's cool, but not necessarily.
Yeah. So in this case, it's really just an illustration.
And you can't make them crash. If you
can't
crash
click
them,
on
then that would be
If you
fun.
could click on them, make them slow.
No, you can't click on the car.
That would be so cool.
So, if I click here, this particular panel is how many cars are recalled in 2014. So what is the idea here for this visualization? Exactly. So the idea is that you show like the relationship between a part and a whole, and the idea is, of course, that this should show you that there's a lot of cars that are recalled. Anybody has a comment on this?
It's hard.
The coloring might bias it a little bit because we pick out red so much better than gray.
Exactly. Yeah. So this here is probably intended to bias people. Like it's just an overwhelming effect. So if we had red and blue, we wouldn't perceive the red as big, but this is a very strongly saturated red color versus a gray light color. So what do you think is what's the point of the animation here?
Really just make it look cool.
I guess it's trying to give you an idea, like if you were to look at a road with cars driving on it, all these red cars would be cars that are recalled, and that looks like a large number, especially because of the red color, obviously.
Yeah.
But it gives you kind of an idea of, in practice, what you like, try and put it in context, I guess.
Yes. So do you think this is easy to understand?
No.
Wow, okay. So this one here. So what do we see here?
It makes it look like GM is doing much better than the other competitors. But it's super biased.
Yeah, so there's a couple of things that are wrong here. So first we have 63 million vehicles here on top, and this also includes those down here. So it's not only a part whole. And then the other thing is, of course, that we have Honda and 9 others. Compared to GM at the bottom here. But of course, the reason for them was this is because of this one fault in these airbags, which kind of caused this rise in recalls. So what do you think about this separation into the various categories?
Well, so it kind of ignores like the biggest point, I think, which should be like the number of deaths, because it looks like there's a lot less of a problem with GM, whereas like 42 people died there, whereas above only 5 people died, but there's a lot more cars coming across the screen.
Yeah.
So it's not like representing the correct information.
That is definitely true, yes. So, a question from a perceptual point of view. Sure.
Also because they're using like a random number generator to generate the small numbers of GM, like the distribution changes. Like right now there's only 2 cars on the screen, but sometimes there's more.
Yes.
I also, like, 18 is a little less than a third of the 63, but for me, that doesn't even look like, I mean, that looks above 50%.
Yeah.
Of that, like, it's so
Very
hard
good
to tell
point,
that
yeah.
it's
So this tells you that this isn't a good visual representation. This is supposed to be more than 3 times as much. We don't perceive it as such. We maybe perceive it as 70% of it or something like that. So, can you suggest improvements? How would you redesign this? That's the right answer to all of the questions we discussed. Sure, you could use bar charts. But I guess one thing that I would do here is at least to somehow, like there's a lot of textual information, you can't really read this without reading this in detail and use a lot of space for unnecessary stuff, so maybe you can come up with something that uses your available space a little bit better for the data. Bar charts will work, there's other things of course that you can do. But this brings us to the end of our class, and we'll see you guys on Thursday, and we will continue with perception and talk about data.
Well, if I need something that conveys whatever I want to say, but not actual information, I'll just look up the New York Times. Your visualization guys are great at that.
I feel like a little frog should be jumping across the street.
Like if the cars were like all sitting still, like then it would be fine, I think. I don't know.
That could have done something better.
Probably doesn't end any better.